like to thank Alex and Carlos for organizing this meeting, which is actually the last of a series of meetings organized here at Villa Tambosi, trying to connect the community of cold atoms and high energy and nuclear physics. And we really hope that this effort will be productive in terms of possible collaboration, or in any case, in exchange of information and knowledge. So my talk, as you see from the title, which by the way, should how?
Maybe you should do it. Title.
Okay.
Sorry to interrupt, but we are not seeing the screen shared. We can see in the camera, but the slides are not being.
You don't see. Okay, try to go on. Okay.
So as you see from the title, I will discuss here properties of sound propagation and the behavior of superfluid density in ultracold atomic gases. By the way, I find that especially concerning sound propagation, this is a topic of high and recent important interest in the community of neutron metal and the neutron stars. And just looking at the internet, I found a series of very exciting and interesting papers written in the last 2-3 years on this topic. Here I will concentrate on the problem for ultracold gases, and I would like to first to remind you, everybody knows that in classical gases, sound propagates as a consequence of collisions, which ensure the achievement of hydrodynamic regime. And this provides this famous expression for the sound velocity in terms of the adiabatic compressibility. In the quantum world, which means at low temperature in the case of ultracold gases, sound exhibits very different and interesting features. In particular, its propagation is deeply affected by interaction, superfluidity, by the dimensionality, by the breaking of Galilean invariance, and the supersolid effects, which are all topics of large interest in our community. What about superfluid density? This is a key parameter characterizing transport phenomena. Its value cannot be determined studying the thermodynamic functions at equilibrium, and it requires the development of transport phenomena, an accurate description of transport phenomena. What is the main goal of my talk here? And the major question is, can the superfluid density be extracted from the measurement of sound velocity in a quantum gas? Because the superfluid density is expected to be a crucial parameter, but the problem, there are no systematic and measurements of this quantity. And so to the extent that superfluid density influences and the behavior of propagation of sound, the hope is to obtain information on the superfluid density by the measurement of the sound velocity and propagation of sound. So let me first, in this context, remind some old and recent collaborations that I will cite during my presentation, which involves collaboration with the Innsbruck people in connection with the propagation of sound and the unitary Fermi gas. The study of the sound propagation in two-dimensional systems and the Berezinski comes to this transition with particularly with Tomoki Ozawa, who was a postdoc here. Then the propagation of collisionless sound in 2D Bose gases. This is a collaboration that was driven by Miki Ota, who was a PhD student here and now is in Japan. And then a long-standing collaboration with Giovanni Martone on spin-orbit coupled gases and supersolidity. And more recently, collaboration with Sandro Stringari, who on the behavior of the superfluid density in connection with the famous Leggett's upper bound for the superfluid density and how this upper bound behaves in our physical systems. So the plan of the talk, I hope to be able to exhaust it, at least the first part, but I want to say something about the second part too. In the first part will be connected to the final temperature behavior. And in particular, I will start from the superfluid, Landau superfluid equations for first and second sound, and the discussion about the determination of the temperature dependence of the superfluid density in 3D and 2D quantum gases obtained from the measurement of second sound. So this discussion may address to what have been the recent experimental advances in this direction, which cover both fermions, bosons, and high and low dimensional systems. The second part is devoted to the behavior at T equals 0, where usually the superfluid density is expected to coincide with the total density, but this is true only if the Miltonian of the system does not break, for example, translational invariance, or only in general Galilean invariance. And in this case, the comparison with Leggett's upper bound is particularly interesting and illuminating. So let us start from the famous two-fluid Landau hydrodynamic equations, which consist of an equation of continuity, an equation for the entropy, an equation for the phase of the velocity, the superfluid velocity, and an equation for the current. Practically all the ingredients except the superfluid density are ingredient which enter the equation of state, and so like the entropy, the specific heat, and this quantity should be known in order to solve this equation, of course. And so the idea, if you want to extract information on the superfluid density as a function of temperature, is to invert this equation and to measure the velocity of sound and to extract from this equation the value of the superfluid density, which is the real unknown in general in many body calculations and the thermodynamic considerations. At zero temperature, this core equation reduced to two equations because the equation for the entropy disappears, of course, and the equation for the superfluid velocity and for the current becomes equivalent at equals 0. And these two equations are called the rotational hydrodynamic equation, which follow from superfluidity and are known to reproduce an impressive amount of physical phenomena that have been investigated experimentally and theoretically in the case of ultracold gases, like the problem of expansion, the problem of collective oscillations, and many other features. Landau equations for two-fluid hydrodynamics. So I'm going back now to the final temperature case. Give rise to two solutions below the critical temperature. You have a first sound solution where the superfluid and normal fluids move in phase, and the second sound where they move out of phase. And in systems characterized by a small compressibility, and in this case, I consider liquid helium-4, which is the historical reference, of course, for the applicability of these equations, and the strongly interacting Fermi gases, second sound reduces to an entropy wave, and in particular, its velocity is fixed by the superfluid density. So to the extent that you can apply and use this equation, and you know the thermodynamic quantities that enter in here, measuring the second sound velocity, provides access to the superfluid density and to its temperature dependence. What is the situation in helium? Helium is an ideal case where the separation between first and second sound is very, very strong because of the very small compressibility of the system. And the two velocities have been measured using different techniques, different approaches. From this measurement, one can extract, one can obtain an important information on the superfluid density. In helium-4, the information on the superfluid density actually comes not only from the measurement of second sound, but also from the moment of inertia with the rotating bucket experiments, and the two methods provide a perfect agreement. And so situation is under control perfectly in the case of helium-4. Now, the Fermi gaseous unitarity, 3D Fermi gaseous unitarity, is probably the best configuration for making comparison with the helium. So because this is the system realizing in cold atoms with the lowest compressibility and with strong interactions. Where strong we mean in the sense of the value of the scattering length, which is very large and provides the unitary limit. So now we have already heard several talks on the 3D unitary Fermi gas, so I don't need to say too much. Just the interesting feature of this system is that the absence of interaction parameters implies that the thermodynamics obey a universal law, where which is written here in terms of the pressure, and as a function in particular of a dimensionless universal function, which is fp of x, where x is the parameter mu over kt. And since these equations do not depend on coupling parameters, one expects that this equation plays a universal application, and in particular, as was stressed also here in previous yesterday, the day before yesterday's, in neutron matter, we expected that the unitary Fermi gas, at least for spin 1/2, so which means exactly neutron matter configuration, a good approximation, even if in the case of nuclear physics we cannot tune the interactions at wish as we can do in the case of the ultracold gases. So all the thermodynamic functions, entropy, compressibility, specific heat, etc., can be expressed in terms of this universal function, whose measurements and whose calculation represent a challenging, let's say, topic in our field. If we want to calculate this function, theoretically, one needs very sophisticated many-body approaches, which have not been, in my opinion, completely exhausted by our community, because it's not easy to work with the unitary Fermi gas at final temperature in a reliable way. There are important results, as for example, the value of the critical temperature, but in general, we don't know so much about the thermodynamics of these systems. And experimentally, from this point of view, I've made an important breakthrough with the experiment by the group of Martin Zierlein, where they were able to measure the function, the fundamental function I was speaking about, this fp function, and from it to extract all thermodynamic properties. And in particular here, you can see the compressibility, the specific heat, and this the calculation of the pairs of superfluid pairs, which correspond to the analog of Bose-Einstein condensation in the case of Fermi systems. Experiments are consistent provide this value of the critical temperature, which is the one of the highest, if not the highest, case in terms of relative value with respect to the Fermi temperature of the critical phenomena for superfluidity in a Fermi system. And then this is an agreement with many body predictions. So many body calculation employing different approaches, also from the people, from some of the people involved in this meeting, are very remarkable, and they are in good agreement. And so the value of the critical temperature is under control. But there are many other things like the thermodynamic functions, and in particular, as I was, which is the main topics of my talk, the superfluid density is not so much explored in this context. So the universal function, as is said, give access to all the thermodynamic functions except to superfluid density. And so the experiment of Zwirlein was not able to say anything about the temperature dependence of the superfluid density. And how can one measure, if you take the experimental point of view, the superfluid density? But according to what I said before, the simple answer, but not easy to realize, is to measure the second sound. And in particular for system with a small compressibility, you could have access to the superfluid density. This was the main motivation for our collaboration with the Rudy Graham team in Innsbruck. And by the way, here we are on the roof of the physics department in Innsbruck. So they tried to obtain the coldest conditions on the roof. They were not enough for our Fermi gases, but in any case, this helped in providing psychological motivation. So I don't explain all the non-trivial technologies needed to measure this, because to measure first sound, essentially you have to apply a laser pulse in the center of the trap, and then to see the propagation of the wave. To measure second sound, you have to apply a heat pulse in the center. And the problem with at that time that if you want to see what happens to this heat pulse during the time evolution, you cannot. It was not possible to measure the local temperature, but it was possible to measure the density. And since the system is not completely incompressible, has a small compressibility, so much, and is much more compressible than helium, you can use this factor to measure the velocity of second sound. At the same time, since the system is not perfectly incompressible, you cannot use the simple Landau equation relating sound velocity to the superfluid density, and you have to solve completely the four hydrodynamic equations, with a major additional difficulty that these systems were confined in an harmonic trap, and so you had to transform the information obtained in this experiment to uniform 3D, which is in principle possible, but requires an inversion of some thermodynamic relations, which is not completely trivial. The interesting thing that the dash of the line here represent the region separating the superfluid from the normal part, and this is possible to see this because the system is trapped in a harmonic trap, and so the density in the borders is smaller than the center, and so the system is less cold, relatively cold in the tails. And you see that fifth sound, which shows up with the peak in the density, small peak in the density, propagates also beyond the superfluid part, while the second sound, which is the pressure, it corresponds to the pressure of the density, because this is the consequence of the mechanism of excitation, does not penetrate the superfluid part, and this is an important argument for confirming its nature. So from this measurement and the real tour de force that I don't want to present here, not to bore you, but it was really the main, by the way, main contribution that we gave to this collaboration. It's possible to extract the 3D superfluid deflection, and we obtain this result. And it's interesting to compare this result with the behavior that is known in superfluid helium, and with the Bose-Einstein condensation of usual ideal non-interacting Bose gas. So these are important comparisons. And I would also like to stress that this measurement represents the first measurement of the superfluid density in a Fermi superfluid, because in helium, this problem was tackled experimentally only in the case of helium-4. And so, while this is the first Fermi superfluid where it was possible to measure these things. I said this was a relatively old paper, but in the meantime, people, experimentalists, have improved a lot their investigation. In particular, again, the group of Martin Zwirling, they did an important effort thanks to the availability of box potentials, where you reduce one of the problems to extract the information coming from the harmonically trapped configurations. And this was an important improvement, but the second, I would say, conceptually speaking, more important, is that they were able to measure locally the temperature with the proper techniques, with the thermometer techniques, so that it's possible to check locally what happens to the temperature, what happens to the density, and what happens to the entropy, using this formula, which is exact for the unitary Fermi gas. And in this experiment, which is not yet published, Martin Zwirling presented a couple of times in conferences. I got his authorization to show the results here, because it's always delicate point. And this is the most interesting figure that I found, where when you excite second sound, you see clearly that entropy changes for different values of temperature, very low and close to the transition. While first sound, there is no change of entropy. While if you go to the density, you have practically the opposite. The density variation characterizes propagation of fifth sound and not so much of second sound. And so this represents a proof of entropy and density nature of second and third sound, respectively. There is another important paper that I would like to show, that it was published 1 year ago by the group of Denschlag. I think the experiment was done in Ulm, but I'm not completely sure. And in this experiment, they explored using techniques very, very similar to the ones that we explored in Innsbruck. They explored the crossover with in a systematic way, measuring the second sound velocity along the crossover, and at unitarity. Of course, the value of the sound velocity reaches its maximum, but also the error bars become larger. So now I would like to move to second question. What happens to second sound in a weakly interacting Bose gas, which is the second big important class of systems that we have in our cold gas community. So theoretically, the study of second sound has a long story. In particular, Griffin, Nikuni, and Zaremba wrote important papers in the past. And the main difference of 3D Bose gases with respect to helium on the unit of Fermi gas is that these systems are very, very highly compressible. And so you cannot use the Landau formula to extract the superfluid density. On the other side, we know theoretically that superfluid density coincides with the Bose-Einstein condensations, except at very low temperature or close to the transition. And so what we expect is a situation like this, where we have an hybridization between first and second sound, and second sound at final temperature here. It can be seen as a continuation of Bogoliubov sound with the temperature dependence of the condensate fraction, which is essentially the superfluid density. And so this is a simple formula which can be shown to be very accurate for describing second sound. The problem of measuring these things, however, is not trivial, because in dilute Bose gases, collisions are very rare. And it's very difficult to reach the hydrodynamic conditions. And I didn't point out explicitly, but now it's the time to do, that the applicability of these two fluid hydrodynamic equations requires in a crucial way the assumption that the thermal component, the non-superfluid component, is in a hydrodynamic regime. And this is not easy for cold gases. And nevertheless, in Cambridge, the group of Azibabic, they were able to realize for the first time this measurement. And this is a paper, I think, not yet published, which agrees with theoretical prediction for the sound velocities and for the, of course, also for the superfluid density. Of course, in this case, obtaining information on the superfluid density is not so crucial, because we know already what to expect also from a theoretical point of view. The problem it becomes more interesting concerning Bose gases if we consider 2D Bose gases. Two-dimensional Bose gases, we know that there is no Bose-Einstein condensation, but the superfluid density is not vanishing. This was explicitly pointed out also yesterday. And we have a jump at the transition, the Berezinski, the Nelson-Kostelis jump, which provides a relation between the critical temperature and the superfluid density at the transition. Calculations of the superfluid density have become available. In particular, the most important series of work were done by Prokofiev and Svistunov using normalization techniques, which applies rather well to relatively weakly interacting Bose gases. And the question is, can we measure this superfluid density and the jump of the transition? And we attack this problem with in a paper with Tomokazawa, and we use the thermodynamic functions calculated by Prokofiev and Svistunov. And using the Landau equations, we extracted the behavior of first and second sound. What's interesting that both second sound and fifth sound have a discontinuity in the transition, but the most important point is second sound, because this transition means that above TC there is no sound, second sound anymore. I'm almost on the end, unfortunately only for the first part, but not on, no worry. The first experiments on propagation of sound in two-dimensional Bose gases were attempted by the group of Jean Dalibard a couple of years, 3 years ago. And, but in this case, they used the rubidium atoms, which are not enough interacting to ensure the hydrodynamic regime. And they observed that the sound propagates well above second sound. What we hope for second sound, the propagates also above TC. And this actually was shown also in a theory paper that we did in Trento, that this sound is a kind of zero sound in some sense, like in Fermi liquids, where you have a strong Landau damping due to thermal effort, but but there is no hydrodynamic regime, and so no applicability for the two-fluid hydrodynamic equations. Only very recently, this problem was achieved, and in particular, again in Cambridge, in the group of the Babbage, they used a potassium gas with large coupling constant. Just to give an idea, the coupling constant used in Cambridge is 0.6, the relevant coupling constant 0.64, to be compared with the one used in previous Dalibor experiment, almost a factor of 4. And in this way, second sound was measured. They obtained the excitation of 2 peaks, first and second sound, and above TC, the clear evidence for a diffusive nature of the excitation, which is consistent with the usual many-body thermodynamic considerations. Starting from this experimental results, and you inverting the Landau hydrodynamic equations, it was possible to extract these are the results for the second and fifth sound velocities. And these are the results obtained for the superfluid density, which essentially prove what we predicted some years ago about the second sound velocity at the BKT transition. So I understand that my time is finished, and so if I have 1 minute, just to no minute, so just to say that as I said at the beginning, at 0 temperature, if the system is Galilean invariant, you expect the superfluid density is equal to the total density. But this is not true if you have, for example, an external periodic potential, or you have a spin orbit coupling, which violates Galilean invariance. And in this case, we calculated explicitly the superfluid density, and we compared with the famous Leggett upper bound, which was discussed in this beautiful paper. And we obtain, for example, in the case of periodic potential, a perfect matching between the superfluid density calculated using Landau, using Leggett approach, and using the behavior of sound velocity. And similar things were done for the spin orbit case, but I have not the time, and maybe if somebody is interested, I can discuss. So what are the main conclusions? The main conclusion that the recent experiment on sound propagations have opened a new perspective in the measurement of superfluid density in systems of different dimensionality. At finite temperature, the relevant information comes from second sound. At 0 temperature, you have important effects due to the breaking of Galilean invariance. Some perspectives, it will be important to study the behavior of second sound in 2-dimensional Fermi superfluids, where very little is known, and in quantum mixtures, where one should use clear fluid hydrodynamic equations. And concerning 0 temperature, it will be interesting to study the propagation of sound and reduction of superfluidity in the presence of the disorder. Thank you for the time.